At Dynamic Alpha Automotive Technology, we are excited to introduce the Dynamic Flow engine, a breakthrough that redefines the traditional four-stroke engine with an innovative valve configuration. Currently, medium-speed marine diesel four-stroke engines achieve peak thermal efficiency of around 42%, while high-speed four-stroke diesel engines in industrial trucks range from 28 to 38%. Gasoline engines in cars and light trucks only reach about 25% thermal efficiency. Our revolutionary dynamic flow engine is designed to increase thermal efficiency in four-stroke engines to an impressive 48%. This improvement has the potential to significantly reduce fuel consumption and carbon dioxide emissions across the transportation sector. As two-stroke and four-stroke piston combustion engines remain essential to global economies with demand expected to rise, advancements in thermal efficiency represent a tremendous opportunity. By enhancing engine efficiency, we can help reduce fuel consumption, lower greenhouse gas emissions, and mitigate NOx pollution. The dynamic flow engine could potentially save billions of gallons of fuel and prevent the release of hundreds of millions of metric tons of carbon dioxide each year. Challenges with conventional four-stroke and two-stroke engines. Two-stroke engines are characterized by a high gas flow rate but a short gas flow duration. In contrast, four-stroke engines feature a medium gas flow rate with a longer flow duration. Two-stroke engines can achieve up to 48% peak thermal efficiency at low speeds, such as 300 RPM in large marine diesel ships. However, due to the short gas flow duration, this efficiency cannot be replicated in smaller, high-speed two-stroke engines. As engine speed increases, the thermal efficiency of two-stroke engines drops significantly. Four-stroke engines, on the other hand, have a lower gas flow rate but benefit from longer flow durations. This allows them to maintain more stable thermal efficiency as engine speed increases, though their peak efficiency typically tops out at 42%. Four-stroke engines are commonly used in smaller, higher-speed applications due to their ability to sustain efficiency across a broad RPM range. At Dynamic Alpha Automotive Technology, we've discovered that by increasing the gas flow rate in four-stroke engines, they can achieve a peak thermal efficiency of 48%, comparable to slow-speed two-stroke engines. Additionally, the longer gas flow duration of four-stroke engines allows them to maintain this higher efficiency over a wider range of speeds. Our dynamic flow four-stroke engine boasts 50% greater intake airflow and 135% more exhaust gas expulsion than conventional four-stroke engines, enabling higher peak thermal efficiency and maintaining better efficiency across the RPM spectrum than both current four-stroke and two-stroke engines. Valve configuration and engine design limitations. In modern four-stroke engines, intake and exhaust valves are positioned on the cylinder head with limited surface area due to the cylinder diameter. Larger cylinder diameters provide more surface area for bigger or more intake and exhaust valves, which in turn can boost power output at higher RPMs by reducing gas flow restrictions. One proven method to improve thermal efficiency in combustion engines is by adopting an undersquare design, where the bore, cylinder diameter, is smaller than the stroke, piston travel. To maintain the same compression ratio, decreasing bore diameter requires a corresponding increase in stroke length. This results in a more efficient engine with a smaller bore, but also reduces surface area for intake and exhaust valves. Consequently, undersquare engines, while more efficient, experience more gas flow restriction at higher RPMs, leading to reduced horsepower. Another way to enhance thermal efficiency and achieve cleaner combustion is by adopting a more efficient combustion chamber shape. Many modern four-stroke engines use a pent-roof combustion chamber, which allows for larger valves and thus higher power output at higher RPMs. However, the most efficient combustion chamber shape is more spherical, as it promotes more complete combustion, leading to higher energy extraction from the fuel and cleaner emissions. The downside is that a spherical chamber requires more surface area, limiting the size of intake and exhaust valves, which in turn reduces power output at high RPMs. In summary, while undersquare engines and spherical combustion chambers can significantly improve efficiency, they introduce trade-offs in terms of gas flow and horsepower at higher engine speeds. Dynamic flow engine. Enhanced gas flow capacity. The dynamic flow engine revolutionizes traditional engine design by relocating the intake and exhaust valves outside the engine cylinder and combustion chamber. This innovative placement allows the valves to be larger, which increases the gas flow rate. Additionally, the timing of these valves is no longer constrained by the engine's operational cycle, enabling more efficient airflow. The dynamic flow engine introduces a new valve type known as the main cylinder valve, which performs dual functions, acting as an intake valve during the intake stroke and as an exhaust valve during the exhaust stroke. Because these dual function valves are more numerous than the singular intake or exhaust valves in conventional four-stroke engines, they allow for a significantly higher gas flow rate, comparable to that of a two-stroke engine. As a four-stroke cycle engine, the dynamic flow engine retains the longer gas flow duration characteristic of four-stroke engines. By combining a higher gas flow rate with extended flow duration, the dynamic flow engine achieves a much greater overall gas flow capacity than current conventional four-stroke and two-stroke engines. Dynamic flow engine with an undersquare design. Thanks to its larger gas flow capacity compared to conventional four-stroke and two-stroke engines, the dynamic flow engine can adopt an undersquare design, where the engine stroke is longer and the bore diameter is smaller, to achieve higher efficiency without sacrificing horsepower at higher RPMs. In this design, the smaller bore requires smaller main cylinder valves. However, because the dynamic flow engine uses more numerous main cylinder valves than conventional engines, it can maintain sufficient power output despite the smaller valve size. As a result, an undersquare dynamic flow engine can deliver comparable horsepower to an oversquare conventional four-stroke or two-stroke engine, while offering the added advantage of significantly improved thermal efficiency. Dynamic flow engine with spherical combustion shape. The dynamic flow engine's enhanced gas flow capacity enables the adoption of a more spherical combustion chamber, which leads to greater efficiency, cleaner combustion, and reduced emissions. A spherical combustion shape being more centralized requires additional cylinder head surface area. However, thanks to the use of numerous main cylinder valves, the dynamic flow engine can reduce valve size to accommodate this efficient combustion chamber shape while still delivering high horsepower at elevated RPMs. In essence, a dynamic flow engine with a spherical combustion chamber can produce comparable horsepower to a conventional four-stroke engine with a pent roof combustion chamber, but with significantly higher efficiency. Additionally, the innovative valve design of the dynamic flow engine eliminates the need for many external components found in traditional engines, such as throttle bodies, external secondary air injection systems, variable valve lift systems, and external EGR systems. This streamlined design results in a more efficient, compact engine. Traditional gasoline engines suffer energy losses of 5 to 10% due to throttle valve pumping losses. The dynamic flow engine's design removes these inefficiencies, potentially increasing efficiency by 10% simply by eliminating throttle valve pumping losses. With its novel valve system, the dynamic flow engine is poised to revolutionize modern combustion engine design.